Lesson 3.3. What happens when we have functions that are being multiplied or divided? We have different rules for each of those. We start with functions being multiplied. The derivative rule is called the product rule. And what you do is you take two functions that are being multiplied together. In this case, it's u times v. Both would be written in terms of x. It's just we're letting u be some function of x and v be some function of x. So its derivative goes like this. You keep one of them the same, multiply it by the derivative of the other, and then they swap roles. You take the derivative of the first, because you haven't derived it yet, and you keep the second the same. So it's like a little flip-flop. One stays, one's derived. Plus, flip it around. An example that illustrates the product rule and why this crazy formula works is this one. Just two normal polynomials being multiplied together. Option 1 would be to use our algebraic skills, multiply these all together right here, and then apply the power rule, which we just learned, to get its derivative. But showing you how this product rule works is going into play in option 2. I'm keeping the first function as is, so this is kind of like u, times v prime, so this is the derivative of the second function. So one stays, one's derived, plus, then they flip-flop roles. I took the derivative of the first one now and kept the second one the same. Distributing, we get all the four terms. Combining like terms, note we have a matching derivative. And if you look, this process is much easier than this process. As we go through from here on out, there will be multiple ways to do the problem, and you want to choose the path that's going to be best for you. The quotient rule is a little complicated, but here's how it goes. You take the bottom function as is, then do the derivative of the top function, or the higher function, minus, and they flip-flop roles like the product rule. The only difference is, because we have subtraction, order matters. So it's really important that you start with the lower function as is. And then it's divided by the low squared. There's a little mnemonic device that can help you to remember this rule. And it goes like this. Low d high minus high d low over low low or low squared. So if you say it a bunch of times, it's kind of catchy. Low d high minus high d low, low squared. This will help you because low means the lower function. D stands for derivative of the higher function. So that's the low d high. And then it flip-flops. Here it is in action. I'm going to start with the lower function. D high, the derivative of the higher function, which is 8x, minus the higher function for x squared minus 5, d low, taking the derivative of the lower function, all over the low function being squared or low low. For the simplification of these, we just focus on the numerator and simplify the numerator. Do not expand out the bottom. So we end up with 24x squared minus 8x. The 3 is being distributed, and at the same time, so we have minus 12x squared, and then double negative makes plus 15 at the end, over the 3x minus 1 squared. That reduces 24 take away 12 is 12x squared minus 8x plus 15 all over 3x minus 1 squared, and that's considered simplified for the quotient rule. The next concept is what we call the second derivative. The second derivative means I apply my derivative process 2 times. In terms of a physics connection, the first derivative represents the velocity in a traditional particle motion problem, and the second derivative represents acceleration. Notations for my second derivative are with the double prime notation or with these exponents. It's very careful. You have to be very careful where you put them because this is representing a second derivative. That's the notation for it, as opposed to squaring a second derivative, which would be very different in notation. So that's why the 2's are kind of jagged like that. If you are trying to find a second derivative of a function, my recommendation is to first do the first derivative and kind of do it in order. And notation matters. You have to make sure you are notating what you are doing. So I'm switching it so that y is equal to this expression. Then I'm going to say y prime and then go for the derivative. You would get 12x to the second, and then that's it. Because e to the fifth does not have an x, so this is considered to be a constant. Then y double prime is equal to 24x. This one, the notation again, is 3x minus 8 over x, which is a quotient. But like I said in the beginning, strategy is key. It is much easier to do these out separately, and you're allowed to because of the fact that you're dividing by a monomial. And then if I simplify, because I want to apply my power rule, this is a much easier derivative to take than the previous one is as a quotient rule. So look before you jump in. And as far as notation goes, I'm going to change it up a little bit here and say I can use dy dx or I can use y prime. So if I take the derivative of this expression right here, the derivative of 3 goes to 0, and then this becomes positive 8x to the negative 2. For my second derivative, again, notation is key where you put the 2's to indicate I'm doing a second derivative. And then negative 16x to the negative 3 would be its second derivative using the power rule, or could be written as negative 16 over x to the third. When you are doing derivatives and evaluating them at a point, you should always, always, always do the derivative first, then do your plugging in. So information that I know up here about different functions is given. We'll use that momentarily. I want to find f's derivative in terms of x, and that's a single prime. So the derivative of little f becomes little f prime of x. This is a difference, so I'm going to apply the difference rule where I'm going to do each one individually, but it has a constant being multiplied by the g. Constants are multipliers that get carried along, so this becomes 8 times g prime of x. F's derivative at 3 is now little f prime at 3, which is 5, minus 8 times g prime at 3, which is 6. So we're looking at 5 minus 48, which gives me a negative 43 for that first derivative. This one, I'm noticing, is a quadratic times a function f of x. Unlike the example on the beginning page, I can't put these together because I don't specifically know what the function f is in terms of x. So this is a case where you would have to go for your product rule. I'm going to keep the first one the same times the derivative of the next. And then they flip-flop roles. Derivative of the first one becomes 8x. Keep the second one the same. F's derivative at 3 is going to be 3 squared is 3 squared is 9 times 4 is 36 times f prime at 3 is 5 plus 8 times 3 is 24 times f at 3 is negative 3. Then you can grab your graphing calculators and calculate your answer for that given expression, or you can do it out by hand. To make sure I don't make a mathematical boo-boo, I am going to type it in. And I'm getting 108. The next one is also a product, and you can't multiply them together because we're not given the function f of x. So I'm going to say f prime's derivative is, keep the first one as is, derivative of the second, plus, and then they swap roles. So then f's being derived while g stays the same. To evaluate f prime at 3, I go back up to the top. Little f at 3 is a negative 3, g prime is the 6, f prime at 3 is 5, and the g at 3 is negative 4. So I'm looking at negative 18 minus 20 for a total of negative 38. Quotient rule. Again, I can't divide these out because I, again, don't know the functions, so I have to apply this new quotient rule. It says low first, we take the low function, d high, minus the higher function, d low, all over the low function being squared. Be very careful with your notation. F's derivative at 3. Now we can go and plug in. Oops, didn't leave a good amount of space there. Put it a little lower. So we have f at 3, which is negative 3, g prime at 3, which is 6, minus g at 3, which is negative 4, times f prime of 3, which is 5. Over the f at 3, which is a negative 3, being squared. I end up with negative 18 plus 20 over 9, which becomes the quantity of 2/9. Page 3. We have a quotient again, but there's a little bit more to it. It's a constant minus the function. So again, start with taking the derivative using our new quotient rule. I'm going to take the low, because we always start low, d high, there's the derivative of the top, minus, it's much more entertaining in class than it is probably as an annoying voice on the video here, low d high minus the higher function times, and this one gets students all the time, the derivative of the low. Derivative of a constant goes to 0, so technically it is 0 minus g's derivative, or just negative g prime. That negative sign is from the subtraction, and it's important to keep. Over 2 minus g of x being squared. I want to evaluate it at 3. 2 minus g at 3. G at 3 is negative 4. 2 minus a negative 4 becomes a 6. F's derivative at 3 is a 5. Minus f at 3 is a negative 3. And then g prime is 6, but I want to change it so it's its opposite. Over this quantity of 6 that we just discovered, squared. So we end up with 30 minus 18 over 36, which is going to give me 12 over 36, which is going to give me a third for that derivative. The following notation right here means find the derivative of function y, which is y prime, at an input value of 1. That's what that notation means. So to do that one, I'm kind of looking ahead here and noticing my quotient is really just a monomial. So I am going to take my y and simplify it so that I don't have to combine a product rule with a quotient rule if I can avoid it. This one, that reduces down to 2 minus, and then the 3's cancel, the t is left here, so that's really a t to the negative 1 times t to the negative 2 plus 3. And again, you have choices. You can multiply these together and then take its derivative and evaluate it at 1. I am going to apply the product rule because we're practicing with the product rule. And I'm finding the derivative just in general first. So I'm going to keep option number 1 as is, and the derivative of the second. Plus, flipping roles now, the derivative of the first, negative 1 joins this negative, so it becomes t to the negative 2 times t to the negative 2 plus 3. Instead of doing the algebra here, because we are specifically finding the derivative at a value, I'm going to save myself making an algebraic boo-boo and go right to y prime at 1. And I'm going to plug in the 1. If you have 1 to any power, it's still a 1. 2 minus 1 becomes a 1. Negative 2 times 1 to a power, well, it just stays negative 2. Plus 1 to the negative 2, 1 to any power is 1. 1 to any power plus 3 becomes a 4. I am less likely to have an incorrect answer because I didn't do the algebra here and make a mistake algebraically and then plug in and have an incorrect value. But again, there's lots of choices. The last problem. You cannot avoid, again, this notation is equivalent to finding y's derivative at the value of 1. This one I cannot divide out because it's a binomial. So I'm going to go through its derivative in general and then plug in the 1. Because the quotient is one factor and that quotient is being multiplied by a polynomial, then that means that this is going to be a product rule because you first must have a product and the quotient is only one of those two factors. How that works, I keep the first one as is and I'm deriving the second. Here's my quotient rule. I'm going to take the low d high minus high d low is 1. All over t minus 8 squared. Plus, in round 2, this one is derived, so it's going to be 20t to the 4th minus 3t squared, and then the second stays as is. Now it looks pretty awful, and again, looking before we jump in, you have choices. You can simplify all this stuff and put it all together, but if you look ahead, I'm evaluating it at 1. So I'm going to say y's derivative at 1, avoid the simplification, and simplify after I have it as numeric values. 4 take away 1 gives me a 3. Over here, 1 minus 8 is a negative 7. Negative 7 times 2 is a negative 14. Minus, plugging in the 1 here, gets me a 9. All over that negative 7 being squared, which is 49. Plus, putting in my 1, 20 take away 3 is 17. Plugging in my 1, I have 9 divided by negative 7. That becomes negative 23 tripled, which would be negative 69 divided by 49 minus 9 times 17, 63, 153 divided by 7. And at this point, we'll grab our graphing calculators. You could have grabbed the graphing calculator for the first part as well and just done the whole thing with the graphing calculator, and you would have been okay. So negative 69 divided by 49 minus 153 divided by a 7. And then let me show you this. You can, I don't know if you're aware of this feature on the graphing calculator, that's your decimal, but I'd have to round and lose accuracy. I don't want to lose accuracy in calculus. So I'm going to go math, hit enter for the fraction. It'll convert the answer into a fraction. So this is my final answer, negative 1140 over 49. And yes, there are features on the calculator that will do derivatives at a point for you. I'm just telling you right now, I am going to be looking for these derivatives first, the plug-in step, and then you can go right to the answer after that. If you just give me y prime of 1 and just give me that answer, you're not going to get credit for the work on that.